All right, so here is an exercise which is unfortunate in the sense that it should be really easy and really straightforward, but there is a small complication that adds a lot of detail. So the basic idea is that we want to show that a set is Jordan measurable if and only if you can find a partition such that the sum of all rectangles intersecting C and those containing in C, the sums are less than epsilon. And the basic idea here is that if you take all of the so S1 is all subrectangles which intersect C, and S2 is all subrectangles which are contained in C. If you take all the rectangles that intersect C and remove all the ones that are contained in C, what you should end up with is a cover of what you should end up with is a cover of the boundary. And so if you can get a cover of the boundary which is less than epsilon for any epsilon, that means that the boundary has measure 0, and that's precisely what it means to be Jordan measurable. So in that sense, like if it was that simple, this exercise would be very easy because you just state that these things are basically equivalent because you take because if you take S1 and remove all of the sets in S2, then what you get is a cover of the boundary. And that's basically all there is to it. However, there are scenarios that you need to be worried about. Say, for example, let's say we've got a set that looks like this. Let's say that this is our set C. So we've got this like line here. And let's say our set C looks like this. And let's say we've got a cover that looks like this. You've got this rectangle here. Then you've got this rectangle here. So what is the problem here with this cover of this set? So this is going to be the set C, this thing that looks sort of like like a Christmas stocking, I guess. The issue is that the top part of this cover, and of course this would be, we'll call this S1 and we'll call this S2. Actually, let's call it R1 and R2 because R stands for rectangle, and that also distinguishes it from the S's that I use, or that are used here, the fancy S1 and the fancy S2, which are the collections of subrectangles. Oh, S for subrectangle. I'm just going to use R for rectangle. Anyways, so R2 intersects C, but R1 is contained in C. But R1 also contains R1 also contains points which are on the boundary. And so this is sort of tricky because the argument doesn't quite work here because let's see here, if we take this, for this example, like the R1 is in what? R1 is in S2 and R2 is in S1. But if you take all the sets which are in S1 but not in S2, that's going to be only R2. And you don't cover the entire boundary because some of those boundary points are contained in R1. What you need to do instead is you need to cover this boundary by really slim rectangles. And they have to be slim because you need the volume of these rectangles to be small. And that's how you are going to get the result that you need. So that's the basic idea. There is this discrepancy because in order to have, basically what happens is these covers consist of closed rectangles. And a point is in the boundary if and only if every open rectangle contains points both in the set and not in the set. And so it's at that boundary of these closed rectangles that you can get issues. And so we have to spend a lot of time worrying about that. So suppose C is Jordan measurable, I'll abbreviate it like that, then what this means is that the measure of the boundary of C is 0. Okay, so given epsilon greater than 0, let S be a covering of delta C with total volume less than epsilon. So that means that if you sum the volumes of all the rectangles in S, then that sum is less than epsilon. And this is doable because this is what it means to be a set of measure 0. What we want to do is we want to remove any rectangles in S which are contained in C but still ensure that S covers the boundary of C. That's exactly the issue that I talked about at the beginning of the exercise. All right. So if R is an element of this collection S, if R is a rectangle in S, and R is contained in C, so let's assume well, let's state this. First, remove elements of S which do not intersect the boundary of C. This should be sort of straightforward, but you could imagine a scenario where you have a cover of the boundary of C, and the cover, the sets that actually cover the boundary of C have total volume less than epsilon over 2, but then you've just got like a rectangle of volume epsilon over 2 just sitting off on its own somewhere that doesn't intersect the boundary of C at all, and the only reason it's there is that you still satisfy the condition of having something which covers the boundary and having total volume less than epsilon. So we want to get rid of anything like that because we don't want to. We want to make sure that we've only got what we need in S, and that's going to be important in order to break this S that we have here into S1 and S2. Okay, so we've removed anything that doesn't intersect the boundary of C. So then, after doing this, if R is in this collection S and this rectangle R is contained in C, then only the boundary of R intersects the boundary of C. And why is this? This is because if X is in the interior of R and the boundary of C, then R is an open rectangle containing X but no point of the complement of C, and this would imply that X is not in the boundary of C, because for X to be in the boundary of C, every open rectangle containing X must contain points both in C and not in C. So if you've got X in the interior of... Wait, we don't need to do this by contradiction, because if X is in the interior of R, then R is an open rectangle containing X, but So R is an open rectangle containing X but containing no point of C complement. I guess I should say then the interior of R is an open rectangle containing X but also containing no point of C complement, implying that X cannot be in the boundary of C because such a rectangle interior, such an open rectangle exists. Okay, so if R is in S and R is contained in C, then only the boundary of R intersects the boundary of C. So remove R from S and replace it with a cover of the boundary of R with total volume less than the volume of R, which is possible since the measure of the boundary of R is 0. I think this was an exercise. The fact that the boundary of an open or the boundary of a rectangle has measure 0. And if it wasn't an exercise, you can go ahead and prove it. And basically the idea is you just cover each edge of the rectangle with a rectangle which is as thin as you want. But yeah, so what have we done now? We've taken R, we've removed it, but removing R could make it so that this collection S no longer covers some points which are in the boundary of C. So in order to make sure they're still covered, you gotta cover that, you gotta cover the boundary of R, because only points that were in the boundary of R could have been in the boundary of C. The only points in R which could have been in the boundary of C were in the boundary of R. So you cover the boundary of R and you've still included all the points from the boundary of C. And of course we can do that. And we can add these, we can add this cover of the boundary of R into S, and we can do so in such a way that we don't add any additional volume to the sum of the volumes of the elements of S, which is important because then it doesn't make the sum of the volumes of the elements of S any bigger. And so at the end of this, so S, what do we know about it? So S covers the boundary of C. The elements of S have total volume less than epsilon, and S is a subset of, so any element in S, any rectangle in S, it covers something in the boundary of C. Okay, so of course when we're covering the we do this process like everything that I've mentioned that we do, we have to do it every time we change the set. So removing every element of S which does not intersect the boundary of C, you need to do that after you add these sets which cover the boundary of R. Because maybe only some, like if we look at this example up here, if you were to have this rectangle here as well, well, I guess that covers points from the boundary of R as well, or boundary of R1. But anyways, basically you need to do this process for all these sets, and what this does is it ensures that every set in S intersects the boundary of C. But it also ensures that no element of S is contained entirely in C. And so let's see here. What are the elements of What's a set of rectangles which intersect C? Well, that's S1. And what are the elements, or was the collection of rectangles which are contained in C? S2. So we've ensured that S is a cover of the boundary of C, and the elements have total volume less than epsilon, and S is contained in S1 minus S2. Actually, no, I'm remembering there's one more thing we have to do. Refine S so that rectangles only intersect at edges here. And again, remove any rectangles which do not intersect the boundary of C. And the reason that we have to do this as well is because we want to take S and extend it to a partition of, we want to extend S to a partition of the domain A. And so that means that rectangles in a partition can only intersect at the edges, the sides of the rectangles. Okay, so refine S so that the rectangles only intersect at the edges or sides, whatever you want to call it. I mean, of course, in 2 dimensions it would be edges. In 3 dimensions it would be faces. I'll just call it edges here. So again, remove rectangles which do not intersect C. Then then what this means is that S is contained in S1 but not in S2. And this was true before, but now we've done it but now it's still true because we've refined this collection and we've thrown out anything not intersecting the boundary of C. So this thing was true when I wrote it before, back before we did this refining of S. But now we can extend it to a partition and have this still be true. Extend S to a partition P of A. Well, wait. What we really want, now that I'm thinking about it, and what I think we have, is this. Because if you've got a set in S, every element of S covers an element of the boundary of C and is not contained in C. So certainly the inclusion that I had in the one direction was true. Now in the other direction, no, let's take this one at a time. So this is certainly true, but now when we extend this to a partition, I guess, okay. S1 and S2 depend on the partition. Okay, so let's actually move this around. So we're going to extend S to a partition of A then S is contained in S1 set minus S2. No, it's going to be equal to. So why is it equal to? Well, we know the one direction, any element in S is certainly going to be in S1, because any element of S intersects the boundary of C. And any element of S is not contained in C. So that's certainly satisfied. So now for the other direction, suppose you have a set which is in S1 and not in S2. So that means that this is a set in the partition which covers the boundary of C and is not contained in C. Then either this set came from S or it came from outside of S. Now, if it came from outside of S, where could it have come from? Well, S covers the boundary of C. So if you're not covering the boundary of C, you can only cover the interior or the exterior of C. So if you're in the exterior of C, then you're certainly not in S. And if you're in the interior of C, then you're in S2. So S1 is automatically not a subset, or any element in S1 is automatically not in the exterior of C, meaning that any element in S1 is either going to be in S or it's going to be contained in C. But any rectangle contained in C is in S2. So if you remove all the elements from S2 from S1, all that remain are the rectangles which cover the boundary of C. And so that's why you have equality. Okay, so we've got this equality. So what this means is that epsilon, remember, this is greater than the sum over all rectangles in S of the volume of R. But S is equal to, S is equal to S1 set minus S2. So this is equal to the sum of anything in S1, the volumes, minus the sum of anything in S2, the volume. And that's because, let's see here, because S1 contains things which intersect S, or intersect C. So certainly you can break let's see, how do I want to say this? So S2 is a subset of S1. S2 is a subset of S1. And so basically, if you take the sum of everything, and if you take this sum here, the sum of R in S1 of VR minus the sum of R in S2 of VR, then what you're doing is you break S1 up into the things which are in S and the things which are not in S. And the things which are not in S are precisely the things that are in S2. And so those parts will cancel out with the second sum. And so all that's left is the elements in the first sum, where you take the sum over all elements in S1 which are not in S2, which is precisely S. And there you go. So that's one direction. We've proven that if the boundary has measure 0, then this sum, then given any epsilon, we can choose a partition such that this difference of sums holds. And again, we had to construct this partition in a very particular way. Okay, so that's a lot of detail, but that's how you have to do it if you want to be very technically correct. However, I feel like if they had done the definitions a little differently, we maybe wouldn't have to worry about the boundaries so much, and we could just do a really straightforward argument and say, like, because this is really the crux of the argument, is that S is equal to S1 set minus S2. Any cover, so if you have a cover of the boundary of C, that should be S1 set minus S2. That's really the crux of the argument. And that should take care of most of it, but of course, because of this technicality, we have to do a lot more detail. All right, so let's see how much detail I can remove for the other direction. For the other direction, given a partition, or no, given epsilon greater than 0, choose a partition. Okay, so this P such that, so we can we can always find a partition such that the sum, I'll just do the sum over S1 of VR minus the sum of S2 VR. We can make this difference as small as we want. So in order to make our lives easier, we're actually going to make it less than epsilon over 2. All right. Set S equal to S1 and then, so what will we have here? If we set S equal to S1, what we're going to have is we're going to have a bunch of rectangles from this partition which intersect the boundary of C. But we might not have gotten everything because there might be points in the boundary of C which are covered only by elements of S2. And for these elements of S2, the elements of S2 that cover the boundary of C, they can only cover it at the boundary of the points. So, okay, let me rephrase this. If you have a rectangle R in S2, which is the only set in S1 or S2 which covers a point on the boundary of C, then that point on the boundary of C must be contained in the boundary of this rectangle R in S2. So what we want is a cover of the boundary of C of total volume less than epsilon. So we start by throwing in all the elements of S1, and then what we do is, we start with S1 set minus S2, which will have total volume less than epsilon. The total volume here will be less than epsilon over 2. And then add a collection of rectangles to S which cover the boundaries of all elements of S2 So let's see here. We're going to add a collection of rectangles. Let's call this S3 to S. Such that S3 covers the boundaries of all elements of S2 and the total volume of Come on, I'm almost done. Don't crash on me. The total volume of the elements should tell my brain not to crash either. The total volume of all the elements of S3 is less than epsilon over 2. And why can we do that? We can do that because the boundaries of the sets in S2, each set in S2 is a rectangle. So its boundary has measure 0. So S2 is a collection of sets of measure 0. So if you take the union of all these elements in S2, it has measure 0. Wait, no. S3 covers, the sets that are being covered by S3 is a set of measure 0. S3 is covering a set which consists of the boundaries of all elements in S2. And every element in S2 has boundary of measure 0. So if you take the union of these boundaries, you're taking a union of sets of measure 0, which will itself have measure 0. Okay. So then what will happen is S equals S1, we remove S2, here, let's make this easier. Define a set of rectangles S3 such that blah. So what we're going to do is set S to be S1 set minus S2 combined with S3. It covers the boundary of C. Why does it cover the boundary of C? Because if you've got an element in the... I feel like I'm repeating myself a lot, but I feel like I need to do this because this is such a strange and convoluted argument. Why does S1 set minus S2 union S3 cover the boundary of C? Because anything... any set in the partition which covers the boundary of C is either going to be an S1 or an S2. Certainly, we take care of all the elements in S1 by so elements in S1 can intersect the boundary of C. That's fine. But for the elements in S2, the elements in S2 can only intersect the boundary of C at their boundaries. And the collection of their boundaries, the collection of the boundaries of the elements of S2 are covered by S3, the elements in S3. So S3 covers boundaries of elements in S2, and then anything left over is in S1 set minus S2. And these are the only things in the partition P which can cover the boundary of C. So if we set S to be S1 set minus S2, take its union with S3, this will cover the boundary of C and has total volume less than epsilon, because if you take the sum of the volumes of the sets in S1 set minus S2, well, that's going to be the sum of the volumes of the elements in S1 minus the sum of the volumes of the elements in S2, because S2 is a subset of S1. And that's going to be less than epsilon over 2 by our choice of our partition. And then S3 is going to have volume less than epsilon over 2 by construction, so the total volume of the set S will be less than epsilon over 2 plus epsilon over 2 equals epsilon. So what this means is that we have a cover of the boundary of C of total volume less than epsilon. And this is true for any epsilon greater than 0. And so the measure of the boundary of C is equal to 0. Okay, so there we go. I think there might be a way to do this where you do both directions at once, because you're doing pretty much the same argument in both directions. Here I was able to make the backwards direction slightly easier because I was able to give myself a little more room. But in both cases, I had to do this really weird thing where I had to worry about the fact that you can have you can't just take a cover of a set, and if you're covering the boundary of a set, you can't just break up this cover into the sets which intersect the boundary and the sets which are contained in C, because like I said, you have those potential issues at those endpoints, and so you have to be really careful. You have to do a lot of work and deal with those. Deal with the boundaries of the sets which are contained in C. You have to deal with those separately. But once you're able to deal with that, or once you understand what you need to do, it's more tedious to write out than it is to understand. So that's sort of, I guess, the good thing here. And hopefully I was able to make clear why that's something that is something that you need to worry about, without making it more confusing by sort of just saying the same thing over and over again in slightly different ways and being a little unorganized. But yeah, this is what you have to do this exercise. And I think you do have to do this. I don't know if there's an easy way around it. But yeah, that's all we have to do for this exercise, so we're done.